Hello everyone and thank you for joining us today. Welcome to Megger's Testing Tactics webinar series. Today's topic is offline partial discharge testing of rotating machines. My name is Michael Fleischer and I'm the Digital Marketing Specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I'll read the questions out during the Q&A segment at the end of the webinar. Additionally, certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Charles Nybeck, Applications Engineer. Also to assist with the question and answer session, we'll have joining us Jeroen Gudertier, Senior Service Engineer. All right, well, let's go ahead and get started. Thank you for joining us today, Charles.
Thank you, and hello everybody, and thank you for joining us. My name is Charles Nybeck, and as Michael said, I'm an applications engineer here at Megger, and today we'll be discussing offline partial discharge testing of rotating machines. Let's go ahead and jump into it. Starting with our presentation outline, we'll first start with an introduction to partial discharge on rotating machines, and then we'll move into rotating machine installation systems, followed by deterioration and condition assessment of stator windings. Then we'll move to look into a couple of normative references, and then move into offline partial discharge measurements in a general sense, followed by typical rotating machine partial discharge patterns. And then we'll look at offline rotating machine testing with the ICMsystem and the ICMflex, and we'll go ahead and summarize it at the end. Starting with our introduction to partial discharge on rotating machines. Partial discharge is a local insulation breakdown of a small portion of the overall insulation system as a result of the influence of an electric field. If your electric field surpasses the dielectric strength of your insulating material, you could potentially have partial discharge activity. And it's due to the electron avalanche that's caused by the required accelerated free electron in this electrical field that results in a destructive high-frequency current impulse and localized heating. And only a fraction of this internal impulse can be decoupled at the stator windings due to the high-frequency signal effects, and this is your so-called apparent charge. And even with today's insulation system design and techniques, a small amount of gas inclusions or microvoids cannot be entirely avoided during the manufacturing process. But it's important to note that commonly used rotating machine insulation materials are partial discharge resistant, resulting in stator winding insulation systems that can more or less tolerate partial discharge activity throughout their life. Partial discharges are inherent to rotating machine insulation systems and serve as an indicator to the insulation deterioration and are one of the root causes of stator failures. When we talk about partial discharge, the performance of the new stator winding has a direct relation to the quality of the used insulating materials, the design of the system, as well as the controlling of the applied processes. And during the online operation, these team stresses play a major role in the partial discharge behavior. And when we mean team stresses, this refers to the thermal, electrical, ambient, and mechanical stresses, and we'll touch on this a little bit later. The gradation strongly depends on, the severity gradation strongly depends on partial discharge location or the discharge site within the winding, which could be the slot, at the overhang, or at the field grading. And we'll take a look at examples of this and how they affect your partial discharge measurement. Since partial discharge activity is inherent to rotating machines, the condition and assessment of the stator winding is not necessarily about detecting any partial discharge, but more or less is about accurately monitoring the development from the initial measurements, focusing on the rate of deterioration as well as any new partial discharge activity that may not have previously been there. Loss factor or tan delta and offline partial discharge measurements are valuable tools to unveil winding deterioration in both factory and field environments. And the major advantage of high-frequency measurements techniques, such as partial discharge, is the possibility to detect the winding defects and fault mechanisms at the early stage. And this early detection allows for intervening for partial repair at the early stage and often avoids the immediate need for rewinding. Now that we've taken a look at an introduction to partial discharge on rotating machines, let's take a look at the rotating machine installation system. The stator winding insulation system requires a certain level of dielectric strength or withstand in order to prevent the insulation shorts during the online operation stresses, and that includes the team stresses we had previously mentioned. The main properties and functions of the stator insulation system are to introducing an insulating barrier between your conductors, ensuring the optimal thermal flow towards a heat sink, such as your magnetic core with your cooling ducts, securing the copper conductors to battle vibrations for your rotating machine, to remain partial discharge resistant for its intended life cycle, ensuring good thermal and mechanical stability, and finally, to protect against moisture and contamination. Here we have an image that shows the evolution of the main wall thickness starting in the 20th century to today. Looking at the first generation insulation systems, these were based on natural or organic materials in combination with natural impregnation agents and resulted in single wall thicknesses of 15 millimeters. Now, in the early 40s, this changed to mica splitting main wall insulation in combination to asphaltic resin bonding agents. And then due to the growth of machines in World War II, these bonding agents were necessary with better thermal properties and stability. And we can see as the years go on, in 83, we have less than 1/3 of the overall size or width of the single wall insulation. And as we move down to today, we can see that the insulation systems that today are based on the mineral main wall insulation impregnated with high-end, low viscous epoxy resins, resulting in a single wall thickness of only 2.5 millimeters, while still achieving the electrical stress rating of 3 kV per millimeter. As we mentioned, today's insulation system utilized the epoxy mica system, where the epoxy resin is your high-end, low viscous thermosetting polymer. It has a breakdown strength of between 20 and 26 kV per millimeter, though it's important to note that this is at atmospheric pressure. And Pauschen's law provides breakdown voltage as a function of distance and pressure. So it means if your pressure was to increase or if your insulation system were to be pressurized, you can actually increase that breakdown strength. Below that, we have mica, which is a group name for the silicate materials where muscovite is generally used. The pure material is shown here in a crystal mica block and can be found in soil and has a breakdown strength of about 120 to 200 kV per millimeter. This pure material is then broken down to flakes as seen here and then used to create these mica-based tapes, which reduces the breakdown to between 8 and 12 kV per millimeter. Now, after the proper curing, these mica-based tapes provide excellent dielectric stability. They provide moisture and contamination ingress protection. They are PD resistant and optimal thermal conductivity and mechanical stability. Taking a look at a motor, we have a low voltage motor here, but the real takeaway is that it's comprised of two main parts, and that is the stator and the rotor. If we take a closer look at that, we have our rotor on the left, which is the part of the machine that will be in rotation, giving your mechanical output for the given electrical energy, and consists of the shaft, the core, and short-circuited copper or aluminum bars. On the right, we have our stator, which consists of the three-phase winding with a core and metal housing. And for the purpose of this presentation, we're going to be focusing on the stator and the insulation for the stator. Now, moving into Stator Bar Design, we'll discuss the different materials and insulating layers that influence the partial discharge measurements. The conductor is not a single conductor, but is distributed into subconductors called strands, as seen in yellow here in the diagram. And this is not only for compact size, but to ensure that the current flows through the core of the conductor rather than the circumference given by the skin effect. And each strand has a thin layer of insulation, as seen in the brown over here, and then another insulation layer in white that is your turn-to-turn insulation. You then have your ground wall insulation, or the main insulation, which is comprised of main mica tape layers impregnated with epoxy resins and is shown in pink here in the diagram. This is a common area for the formation of microvoids after the VPI impregnation cycle. And aside from these layers of insulation, there are still the slot stress grading layer shown in purple, the semiconductive layer in gray, and then the end winding sealing in tan here. Now, it's important to have a good understanding of the stator bar design because, as we'll look at later, The phase resolved partial discharge pattern generated from a partial discharge measurement gives insight into the type of defect and its location within the insulation, which in turn reveals the severity of the defect. Next, let's move into deterioration and condition assessment of stator windings. In the in-service conditions, stator windings are subjected to several stresses. In the machine jargon, we often refer to these stresses as the team stresses, and these combined can impact the speed of the deterioration of your insulation system. And as an example of these team stresses, one could be overloading or with consequent overheating or hot spots as a thermal example, uncontrolled electrical surfaces as your electrical stress, humidity and temperature or contamination as your ambient stresses, and vibrations or structural overhang resonances as your mechanical stresses. Poor manufacturing processes can impact the common operational team stresses, causing acceleration and deterioration of your insulation, as opposed to the normal aging processes, and can result in partial discharge behavior that may develop more quickly. If we look at the case of normal gradual aging, it's assumed that the life cycle of a stator is up to 20 years. However, if a partial discharge fault mechanism develops on a critical position within the winding, this may cause severe damage in only a couple of months. And partial discharge measurements provide insight into these PD fault mechanisms and are excellent diagnostic tools to include in one's condition-based maintenance program. Here we have a study performed by EPRI and IEEE where a combination of over 10,000 machines were analyzed. And it was found by both of these studies that the stator winding related failures accounted for 37% of the overall failure rate. And taking a more narrowed look at this, we have a study of high voltage motors in the petrochemical industry, and where the high voltage motors are broken into two classes of less than 2 megawatts and greater than 2 megawatts. Looking at the high voltage motors that are rated less than 2 megawatts, 57% of the failures were due to rotating machine bearings, while in high voltage motors greater than 2 megawatts, 60% of the failures were due to the stator windings. And this is due to the fact that rotating machines above 2 megawatts utilize sleeve bearings with higher reliability rather than the ball bearings with higher failure rate. And a similar Seagrace study is available from an investigation made on 1,200 hydro generators, and in this particular case, the stator winding insulation damage represented 56% of the overall cases. So this failure root cause investigations really show and emphasize the importance of electrical and dielectric testing to assess the condition of the rotating machine stator windings. And below we have an example of the global recommendation for stator winding assessment, where the factory acceptance test should include offline partial discharge and tan delta measurements to serve as your baseline reference. It's recommended that the factory acceptance test be performed in accordance to the IEC 62 standard frequency range and the compliance test circuit. After that, the first offline inspection is recommended to take place anywhere between 6 to 12 months after the commissioning. This may be difficult to achieve in some cases, but it has the benefit of revealing any partial discharge activity at the early stage that could be a result of the previously mentioned team stresses. Further offline measurements are to be performed every 2 years, or alternatively, coupling capacitors could be permanently installed for online partial discharge measurements every 6 months, combined with a full inspection offline every 4 to 5 years. Here we have a typical scope that includes offline stator winding inspection. First is a visual inspection of the overhang and slot, and a visual inspection should never be overrated, as partial discharge activity leaves behind residue that can be seen visually, and so a visual inspection is really easy to perform and always offers a lot of benefit. Next would be winding resistance and inductance measurements, followed by a surge test if possible. And the surge test may be influenced by the rotor winding, so any deviations in the surge oscillations can be solved by simply turning the rotor. Next is the insulation resistance and polarization index measurements, where the polarization measurement gives insight into the surface condition of the insulation in case of the presence of moisture or other contaminants. Next, we have the optional tests of DC step voltage and the long duration polarization and depolarization tests. These optional tests can be performed, but typically after the polarization test, one would simply move to the dielectric loss factor tip-up and capacitance test, followed by offline partial discharge test. Lastly, you have your AC high pot test, but this is typically only done after on-site repairs such as a re-wedging. Now that we've taken a look at the deterioration and condition assessment of stator windings, let's look into some normative references. While there are currently standards for the high voltage equipment such as power transformers, shielded cable, and switchgear, there are currently no standards that define acceptance criteria for partial discharge testing on rotating machines. This lack of criteria often causes an endless discussion between the owner and manufacturer about proper testing and test reports. Now, it is important, or an important distinction, that rotating machine insulation systems are designed to be partial discharge resistant, while shielded cables and transformer insulation systems are assumed to be partial discharge free. So this brings up a couple of frequently asked questions, such as how much partial discharge is too much partial discharge, or how about defining some acceptance criteria for partial discharge resistant insulation systems? And these questions are answered on both sides. On the one side, you have machine owners and diagnostic engineers that would really appreciate such acceptance criteria. But on the other side, you have the manufacturers stating that they already use high-quality partial discharge resistant insulating materials and optimized impregnation techniques. Also, the lowering of acceptance levels would cause an increase in machine prices due to overly dimensioned installations. So a proposed middle ground could be to maybe work with the manufacturer to evaluate and determine what are acceptable partial discharge levels for their machines. Here we have some normative reference, including the main horizontal standard or an umbrella standard, that is the IEC 6270. There are several vertical standards that stem from this, as well as other technical specifications and guides from IEEE, the IEC, EA, SA, CGRE, and EPRI that include test circuits and procedures, voltage application sequences, test durations, partial discharge bandwidths, calibration circuits, typical partial discharge phenomena, and we'll kind of take a look at these as well a little bit later. But the main documents to take away from this are the IEC 6034, the IEEE 1434, and the CGRE reference 258 and 558. Now that we've covered some normative references, let's take a look at offline partial discharge measurements in a general sense. In this chapter, we have sub-chapters that include offline partial discharge measurements covering the basics, high-frequency partial discharge signal properties, partial discharge measurement versus bandwidth, stator model, the example of machine PD spectra, partial discharge calibration, recommended test circuits, and the test procedure. Looking at the offline partial discharge basics, to perform offline partial discharge, the motor or generator must be taken out of service, and the high voltage cables and bus bar system are disconnected and isolated. The stator windings should be energized using an external partial discharge free high voltage source. And the high voltage source can range from the traditional high voltage transformer to a resonant test set, even a compact power factor test set with integrated high voltage source, or a VLF source, but testing at very low frequencies has its limitations. The measurement conditions differ from normal operations and offline partial discharge tests. For instance, it would be a cold conductor test, meaning it would be under no load conditions. The influence of environmental conditions would be different from the online conditions, such as temperature and humidity, and of course, different electrical field distribution since you're energizing using an external PD high voltage source. Reference measurements should be performed during the factory acceptance test, while an in-depth verification by periodic field testing can be done during an outage or after a trigger by online measurements or from continuous online monitoring. Offline partial discharge measurements are typically combined with the visual inspections, loss power factor and capacitance measurements, as well as DC installation tests. And partial discharge measurements can offer insight into which steps need to be taken for partial repairs, and even more importantly, can be used to verify that the repair was performed correctly. So if you have a measurement and you know that you have a defect, you can go in and perform the partial repair and perform the measurement again, and you should be able to see a difference in your measurement that can confirm that the repair was done correctly. The internal activities within the main insulation generally start as a gas discharge, and the previously mentioned electron avalanche that's caused by the initial accelerated starting electron changes this electrical field and causes the local high-frequency current impulse. Now, the electron avalanche during this discharge causes rise times in the range of microseconds, nanoseconds, or even picoseconds, depending on dimensions and geometry, permittivity of insulating materials, type of gas and gas pressure, and surface conductivity, resulting in a broad bandwidth. For instance, looking at the nitrogen condition, which is essentially your ambient air condition, the rise time is typically in the range of 1 nanosecond, which translates to a bandwidth up to 350 megahertz. Though, due to the fact that the stator winding is a non-ideal high-frequency conductor, only a fraction of the initial signal bandwidth effectively arrives at the winding terminals due to the high-frequency signal properties. Looking at some of these properties, the high-frequency pulse experiences these high-frequency effects while on the way to the coupling capacitors that are installed at the bus bar or the apparatus terminals. And this includes attenuation, which is generally due to the total capacitance to ground, reflections due to changes in impedances, dispersion or resonances and dispersion, and radiation that act at generally the higher frequencies. A basic understanding of pulse propagation and bandwidth selections are necessary to perform the measurement and analysis. While the lower bandwidths are more prone to high frequency noise, but offer the benefit of better coverage to detect partial discharge in the entire winding. And it's recommended that the detection bandwidth for offline testing be less than 1 megahertz, and this is according to the IEC 6270 standard. Here we have an example of partial discharge patterns versus the detection bandwidth, where a 1.2 megawatt 6600 volt asynchronous motor with an internal neutral connection that has a VPI impregnated stator winding was tested offline. Partial discharge measurements were taken and 60-second pattern acquisition was performed using a coupling capacitor, meaning the conventional method was used. Now, it's important to note that for the 3 images we see, this is the same test object at the same test voltage, but performed at different bandpass filters. Looking at the graph at the left, this contains the pattern acquired when performing the test in accordance to the IEC 62 standard with a bandpass filter between 40 and 800 kilohertz. While the middle graph contains a measurement with a medium bandwidth of 2 to 20 megahertz, and finally the right-hand graph with the same measurement up to 200 megahertz. The right 2 plots here do not allow for calibration as they are outside the allowed frequency boundary provided by the IEC 6270 standard. Also, notice the decreasing trend in activity as the bandwidth increases, where in the IEC 6270 compliant measurement we have over 1 million counts. In the medium bandwidth we have just over 100,000, and then in the large bandwidth we have just over 2,000. And we can see a distinct loss in the shape of the partial discharge pattern, where we have a nice symmetrical triangular distribution, and we start to lose that as the bandwidth increases and starts to deviate from the IEC 62 recommended bandwidth. Here we have an example of an offline signal spectrum on an 800 kilowatt 6,000 volts asynchronous motor with an internal neutral connection. Taking a look at the phase resolved partial discharge pattern, we can see a nice symmetrical distribution, and this tells us that the partial discharge activity is within the main insulation or the ground wall insulation. And just to kind of give some background of what a phase resolved partial discharge pattern is this is actually a 3D graph that provides the phase angle, the magnitude of discharge, and actually the color is the repetition rate of the discharge is taking place, where gray is less repetitions and the red is more. And we'll look at a couple of other phase resolved partial discharge patterns a little bit later. Looking at the spectrum analysis, we can see that the signal shows signal strength or available signal up to 5.5 megahertz. This doesn't mean that there's not signal beyond this, but it would require high amplification. But the main takeaway is to look towards the corner frequency or cutoff frequency 1 and measure around here where we have the higher gain. And this is around the 1 megahertz range, which is the IEC 6270 recommended bandwidth. Partial discharge measurements are relative measurement and therefore require calibration. And this is given the calibration requirements are given in the IEC 6270 standard. The calibration should be performed by injection of a calibration pulse into a well-defined magnitude and should be injected at the machine terminals. And then the magnitude can be adjusted at the PD detector for the signal response. And this is to compensate for the overall attenuation in the measurement circuit with the device under test connected. What that allows you to do is say you're injecting 10 nanocoulombs and of a well-defined signal into your setup. And you can go to your partial discharge detector and then calibrate it to that 10 nanocoulomb, and now you have calibrated for the current setup you have. And we'll look at that a little bit more on the next slide. Looking at the IEC 6270 and standard, a calibration is only valid when using a bandpass filter. And that means looking at the requirements there, you have a lower corner frequency or cutoff frequency that should be higher than 30 kilohertz while being a maximum of 100 kilohertz, while the upper corner frequency or cutoff frequency should be below 1 megahertz. And this results in a minimum detection bandwidth of 100 kilohertz and a maximum of 900 kilohertz. The calibration cannot be performed above the 1 megahertz range according to the IEC 6270 standard. And this is typically referred to as a sensitivity check when you're above this frequency range. And the power diagnostic instruments do support the quasi-integration at these higher frequencies. Looking at the offline calibration circuit, we have our rotating machine, and we have our pulse generator or our calibrator connected in parallel to the rotating machine, as well as the test setup, which is comprised of your coupling capacitor to decouple the partial discharge activity, your measurement impedance or conditioning, and then finally your partial discharge detector. For typical calibration for rotating machines are in the range of 500 picocoulomb to 10 nanocoulomb, and this depends on the slot length and capacitance and changes from winding to winding. And also the signal to noise ratio based on the environment in which you're testing plays a role in the calibration magnitude as well. It's important to note that when calibrating, you should always inject as close as possible to the machine terminals, and that for larger machines, calibration per phase is recommended as the windings are not always fully symmetrical. Also, it's important to keep the calibrator lead short as possible to avoid any distortion due to the inductance in the leads. And finally, when performing the calibration, this is only valid for the test setup in its final arrangement at the specified detection bandwidth and calibration magnitude. If these are to change, the calibration should be performed again. Here, moving on, we have an example of the recommended offline partial discharge test circuit, in which we have a motor or generator with accessible neutral, which allows us to energize the complete winding to ground as well as the individual phases to ground. While testing at the maximum voltage is not really possible with the internal neutral connection because the electrical field distribution is the same throughout. Looking over at the right, we have the IEC minimum recommended testing, where you test per phase at the terminals. So looking at the example here, we have our high voltage source, our PD-free high voltage source connected to our U phase, while our untested phases, our V and W phases, are grounded. So looking over here, we have our U2 with our V1 and W1 grounded, and then our coupling capacitor placed at the other end of the winding at the U1 that decouples your partial discharge activity. This provides your signal conditioning, and then your partial discharge detector performs the measurement. Now, you can perform additional tests when you have the accessible neutral by just simply flipping, and you can see now the high voltage is performed or placed at the U1 phase, still grounding the untested phases, and the coupling capacitor is now placed on the other side. And this allows for additional measurements and additional damping effects for a more in-depth inspection. In this example, we have a stator winding that has an internal neutral connection so that when performing the test, the entire winding is under the same applied voltage. Now, at an initial glance, in this case, one would think that there's only one measurement with the terminals shorted together. but this would result in an average measurement that would not give insight into the condition of the individual windings. So taking a look at our inaccessible start point, we have our U1, V1, and W1 for our high voltage, which we can see in this case over here. It's moved for because we cannot access the start point, and your coupling capacitor is placed at the same, so you're decoupling there. But since partial discharge measurements are high frequency measurements, it's recommended to actually perform the measurements on each individual terminal. So again, looking here, we have measurements on each individual terminal, and this provides more insight into the condition of the individual terminals or windings themselves. And taking a look at an example of an offline partial discharge inspection of an 850 kilowatt 10 kV asynchronous motor with an inaccessible neutral, this example really highlights the benefits of performing the partial discharge measurement on each winding terminal, even when you have an internal neutral connection. Looking at the partial discharge of the phases individually, we can see the U and W phase have partial discharge at about 1,000 10,000 picocoulomb. But the V phase is significantly higher, many times higher than that. If you were to perform the measurement on all the phases shorted together, you would get an average measurement, and you wouldn't be able to see these individual partial discharge patterns. So looking at the U phase, we can see signs of floating potential, but looking at the magnitude of the discharge, it's only 8.56 nanocoulomb. As we move to the W phase, we can still see signs of floating potentials, but this is again still only 6.29 nanocoulomb. Finally, looking at the middle phase, the V phase, we can definitely see well-defined partial discharge, and look at the magnitude now, 85 nanocoulomb. So this really highlights the benefit of performing the individual tests on the terminals themselves, providing more insight into the condition of the windings. Here we have an offline test procedure example where insulation resistance and polarization index measurements should show acceptable results before moving forward with your partial discharge measurement. Next is to determine the test circuit according to the suggested diagrams, for instance, whether or not you have an accessible neutral point or not, and then finally calibrate the setup. It is recommended then to condition the winding at the rated voltage for 2 to 3 minutes prior to performing the partial discharge measurement. And what this does is this provides a more representative measurement value rather than applying the voltage and just immediately taking the measurement. As far as the voltage application sequence, it's recommended to perform this, apply the voltage in steps of 20% of the rated voltage up to the rated voltage. So for instance, if it was 10 kV, you'd go in steps of 2, 4, 6, 8, finally 10 kV, and then back down 8, 6, 4, and 2 kV as your applied voltage sequence. And what this does is this allows for the monitoring of partial discharge inception voltage, which is the voltage at which partial discharge starts to take place as you're going up this sequence of voltages, and then partial discharge extinction voltage, which is the voltage at which partial discharge ceases to take place as you go back down. And this offers an advantage because a lowering inception voltage can be a sign of insulation deterioration. When performing the test, a phase resolved partial discharge pattern is recommended to be taken for a minimum of 30 to 60 seconds at each step. And ultimately, the goal is to monitor the discharge magnitude accurately while raising the test voltage, and of course, not to hesitate to suspend the test in case of any uncertainties or unsafe conditions. Next, we'll look at the typical rotating machine partial discharge patterns. Partial discharge in rotating machines can be classified in several different ways. For instance, internal discharge activities that include delaminations in both the main wall insulation or the conductor-bound insulation, or microvoids within the insulation and thermal aging. Another classification could be end winding or overhang discharges in the form of surface discharges due to contamination or bar-to-bar activity, as you see here down at the bottom. And this also, taking a look, you can see the benefit of a visual inspection as you can see residue from partial discharge activity as you do here as well. Another case would be vibrations that are common within rotating machines. Next are slot discharges that can be a result of wedge problems, for instance down here where you have a wedge missing, or from inadequate impregnation during the VPI process. Then you have the slot exit discharges that are issues with the semiconductive layer at the slot exits, and finally external high frequency disturbances. Taking a look at a couple of examples of possible discharge sites that produce their own unique partial discharge patterns. In terms of case 1, you have a spherical microvoid at the corner of the conductor where the gradient is at its highest. This can lead to partial discharge activity that has a very low inception voltage. Looking at case 2, we have a conductor-bound delamination that's typical of setups with frequent load cycling. In terms of case 3, you have an internal delamination here that's in the main wall insulation and not conductor bound, and this is caused by the normal thermal aging. In the terms of case 4, you have a delamination that's located at the slot corona prevention layer that is referred to as the ground wall delamination and results in slot discharges. And finally, case 5 here, you have the case of an internal microvoid that's typical after the VPI impregnation cycle. Getting a more in-depth look at these discharges and looking at their phase-resolved partial discharge patterns, we can see here the typical pattern for a remaining spherical void or air pocket after the impregnation cycle. Looking, we can see the symmetrical distribution tells us that there is no conductor involved in the discharge and that it is within the main bulk insulation, as we can see in the diagram to the right. Now, we can see there is no yellow, which means you have a low availability of starting electrons, or in other words, low repetition within the discharges. And this is typical because freshly impregnated epoxy generally provides limited free electrons. Finally, we can look and see that the difference we have between unipolar and bipolar measurements. And looking at these, you can actually count the number of voids as these arcs. So in the case of this left graph, you have 1, 2, 3, maybe 4 voids within your insulation that allows you to actually count them. And looking at the right, you can see the steepness of this discharge, and this is proportional to the applied voltage over the time, so the dV/dt of your applied voltage at the inception. Moving on, we have an example of internal delaminations at the early stage. And these have higher availability of starting electrons that are provided by the primary void discharge and the chemical deterioration of the insulation. And this can be seen in the distribution with the yellow here showing higher repetition. Also looking at this image, this is what you'd expect of a new machine with a nice symmetrical pattern with no high dV/dTs showing a smooth distribution. Now, taking a look at the image on the right, though, we can see we have a delamination as seen here and here, but also we have the presence of microvoids, as we can see in the arcs here. So this is an example of a phase-resolved partial discharge pattern that allows the properties to determine whether, the type of failure mode. So whether you have just a delamination or delamination and voids, and that's the advantage of a phase-resolved partial discharge pattern. Next, we have conductor-bound delaminations that are typically caused by frequent load cycling and can cause high stress in the contact area. This can produce localized heating and result in hot spots, and otherwise can lead to turn-to-turn failures. Looking at the phase-resolved partial discharge pattern, we can see an asymmetric pulse distribution on both cycles and is dominant in the positive cycles. So looking at the applied voltage, we can see that the phase-resolved pattern is dominant on both examples in the positive cycle. And this partial discharge pattern of the failure is dominant, and it shows a triangular distribution rather than the arcing we saw in the voids. In this situation, the delamination is on the ground wall of the insulation, resulting again in an asymmetrical pattern with dominant negative cycles in this case. The distribution is still a triangular distribution, but one thing to note with the ground wall delaminations and slot discharges is that slot discharges can produce ozone, which in turn cause collateral damage. We'll look at that right now. Here we can see examples of heavy corrosion on space heaters, cooling elements, auxiliary transformers, PTs, and CTs, and this is from machines with closed ventilation systems where the high ozone levels stay trapped and corrode the metallic surfaces. So this kind of shows the damage that can be done not only to the windings of your and insulation of your rotating machine, but also on some of the secondary or auxiliary components as well. Next, we have an example of end winding discharges that are typically a result of contamination or humidity on the overhang, and this results in a symmetrical pattern as seen here again with the triangular distribution. Taking a look at some other overhang partial discharge sources, if we look at the right-hand side over here, we have conduction contamination, as we can see on the windings. And in the middle, we have inadequate spacing between coils. And again, you can see the residue left over from your partial discharge activity. On the left here, we have insufficient grading of the semiconductive layer. And then an example of end winding vibrations, typically due to the startup stage. Moving on with slot egg discharges, the thermal and mechanical stresses from this cause small surface cracks within the semiconductive layer, as seen in the diagram here, that results in surface discharges that start to deteriorate the outer insulation. This results in detection magnitudes anywhere between 10 to 50 nanocoulombs, but as this continues, the small cracks can develop and grow due to the erosion by PD. And we can look at that here where the final stage can result in the semiconductive layer losing contact with the conductive layer, causing heavy arcing. And this arcing is visible and can lead to partial discharge detection values above 100 nanocoulombs. Finally, we have an example of high frequency interference, where in the top example, we have high frequency disturbances introduced by a frequency converter on the same grid. And this can be seen in these lines here that are really not indicative of partial discharge activity. Now the image to the right shows that the use of a high frequency current transformer and the gating function can effectively remove the noise from the measurement. As you can see, you get a nice clear pattern. In the bottom example, we have excitation noise that can be introduced by diode or thyristor firing, as seen in the diagram on the left, or the PRPD pattern on the left. Now again, this type of disturbance can be removed by simply using the high frequency CT and the gating function, resulting in a nice clean measurement. Now that we've taken a look at or discussed the introduction to partial discharge, deterioration within the stator windings, covered some normative references, and actually covered partial discharge testing and rotating machines, I wanted to go over the test setup again, but include some images that can help kind of visualize this test setup, where again we have our high voltage source over here to the right. That could include a high voltage transformer, a resonant test set, or your compact power factor test set with an integrated high voltage source. Then, looking at the next component, you have your coupling capacitor. And the coupling capacitor, in this case, has your coupling capacitor here and your measurement impedance at the base of it for your signal conditioning. Optionally, you could include a preamplifier for additional signal conditioning as well. And this coupling capacitor offers the output of also not only your partial discharge signal, but the high voltage sync that you saw, the sine wave on the phase resolve patterns, where you can overlay your high voltage applied and your partial discharge signal. Finally, the partial discharge signal goes out to your partial discharge detector and then your control software controlling the measurement. Taking a look at this and taking it a step further, we can actually look at the test setup here, where again we have our rotating machine stator winding. We have our high voltage PD free source, in this case a power factor test set with integrated high voltage source. Your coupling capacitor here. You can see your high voltage source applied, and then so you have high voltage applied to your U phase, decoupling the partial discharge activity. Your measurement impedance is at the base again. Your untested phases are grounded, and then your ICMsystem or your partial discharge detector unit, and then your control software. So this is an example of what a test set would look like when completed. Moving on, we'll look at some offline rotating machine testing using the ICM system. The ICM system is an advanced partial discharge detection system and analysis tool, and is available up to 10 channels with simultaneous real-time acquisition. But for testing rotating machine, it's recommended to use the 4-channel system, and we'll go into that on the next slide on the advantage of that. It does offer integrated spectrum analysis with up to 10 megahertz, with both narrow and wideband of 9 kilohertz and 300 kilohertz, capable of time domain analysis as well as measurements in AC and DC voltages, has advanced control software, high resolution 16-bit phase resolve partial discharge pattern, powerful suppression and input sensitivity, IEC 6270 compliant, and is capable of field and factory measurements. Here we have an example of the configuration for rotating machines. Again, this is the coupling capacitor we saw earlier, used to decouple the partial discharge activity where you have your PD output as well as high voltage sink. Here we have an example of the high frequency current transformer that's typically used for noise reduction by the gating function. We have our pre-processing that's typically done with the preamplifiers, where we have the RPA1E that's IEC 6270 compliant, and our wideband RPA1H that's used for spectrum analysis. Finally, you have your acquisition unit, which could be a 2-channel system or a 4-channel system, where the 4-channel system offers the benefit of performing the test at the line side, the neutral, connecting the ground phases, and using the final channel to be used for noise gating. Covering the ICM system software has miscellaneous panels and visualizations, where the single channel acquisition offers advanced trigger function and analog signal conditioning to analyze the phase resolve partial discharge pattern from single channel measurements. You have the multi-channel panel that has advantages of comparing the measurements, since the ICM system takes parallel measurements. You could take these and compare and take accurate comparisons between the multiple channels. Next, you have your spectrum analysis, which we covered before, and offers the benefit of being able to choose the optimal bandpass filter for your measurement, or measuring bandpass. Next, you have the trending functionality that allows for trending of the step voltage while the partial discharge measurement is taking place. The trending file can be reopened, and you can use the phase resolve partial discharge patterns for your reporting, or you can use that trending file to generate a short video for later use. You have the statistic analysis panel jumping forward, you have the 16-bit partial discharge pattern for your high resolution phase resolve partial discharge pattern. Then you have your statistical analysis pattern that provides many different things such as skewness, partial discharge detection level, an IEC detection level, and more. And finally, your time domain analysis that allows for comparison of your 3 stator windings in the time domain. Covering a couple of more additional setups, just some images where we have the ICM system and the ICMflex with a line filter attached to a turbo generator. Next, you have the ICM system in a laboratory environment and power diagnostics in Germany, performing measurements on a frequency-controlled high-voltage motor. Here, just a 4-channel ICM system with a high-voltage setup, and then on-site calibration of the ICM system. Next, we'll move on to offline rotating machine testing using the ICMflex, where the ICMflex is a measurement system for partial discharge, dielectric loss factor, tan delta, and capacitance measurements. It offers a unique design with the acquisition box and the high voltage potential, offering increased sensitivity, is capable of power frequency synchronization between 20 and 510 Hertz, as well as VLF compliant. It's essentially a plug-and-play setup with a high voltage line filter, where down here is essentially just your setup at this point. It offers user-friendly control software with reporting functionality and optional step-by-step guide. Communication is via Bluetooth or fiber optic. It is battery operated for up to 12 hours, and similar to the ICM system, is IEC 6270 compliant and suited for field and factory environments. Looking at the ICMflex software, it has an all-in-one operational panel where you can do advanced recording of tan delta and capacitance measurements. So you have your tan delta and capacitance measurements and a summary table here. It supports 2- and 3-dimensional acquisition, where you have 2-dimensional with just your phase angle and your magnitude in this top graph. And here you have your magnitude, phase angle, and as we discussed, the repetition or the counts in color. The graphs are simultaneously updated, and you offers the trending versus time, where in this example, you have your partial discharge measurement in black, your tan delta measurement in red, and capacitance in green. You have your phase resolve partial discharge pattern, and then your tan delta capability. The ICMflex exports data in several different formats and has semi-automatic generation of report that includes the ability to add your company logo. It adds a data summary table, as well as any partial discharge patterns that were taken during the test. A couple of setups with the ICMflex. Here you have a factory environment test on a large generator winding where you can see the ICMflex and the high voltage line filter. So notice just those two, aside from your partial discharge free high voltage source, are the only things that are necessary. You have a similar environment here, but the test was performed on a hydro generator winding. Here an on-site measurement or a small compact generator, and then an on-site measurement on a motor. The takeaway from this is the ICMflex is capable of measurements on a wide range of rotating machines, ranging from large to small power ratings. To finish it up with a summary, stator winding installation systems are PD resistant and widely tolerate partial discharge activity for several years of operation without being a root cause of failure. And dielectric measurements are important as monitoring vibrations, and partial detection on rotating machinery is a matter of trending and comparing the results rather than just determining if there's something there, because there's no acceptance criteria defined. Sufficient care must be taken to select the bandwidth, calibration procedure, and the correct selection of recommended test circuits. The analysis of your phase resolve partial discharge pattern or PRPD pattern provides essential information about the ongoing type of discharge and its location. And offline measurements serve as an in-depth verification after manufacturing during the first month of operation and during major maintenance outages. And moreover, are an excellent tool to be used for partial repairs. Thank you, everybody, for your attention, and that's going to be it today.
All right. Thank you very much, Charles. So at this time, obviously the presentation portion of our webinar has concluded. We'll now take some time to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the right side of your screen. For those of you that are leaving, when you close your webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there's a field where you can also request a demo or quote on any Megger products. A copy of this presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in 2 business days. You can also view recordings of previous webinars on our website at us.megger.com/webinars and register for our virtual best practices seminar, Power Factor and DFR for Insulation Condition Assessment, this upcoming Wednesday. All right, let's get to your questions. Our first one is going to be for Jeroen. What is good values for partial discharge in high voltage and low voltage motors as per IEEE?
Yeah, well, this is a question that is fairly easy to answer, I'd say. At these days, not IEEE, neither IEC, CGRE, or other groups such as ASA are defining acceptance criteria for rotating machinery. So these days, that's what is actually been missing in the field of rotating machines are acceptance levels, and this is sometimes leading to quite picky discussions between motor manufacturers and customers during the factory acceptance test, because how much PD is too much PD. So unfortunately, there are no values mentioned yet, and we will have to see how this develops in the future.
All right, thank you. While I have you, what is the major difference between offline and online PD tests?
Well, Michael, I think it was briefly explained in the presentation. So basically, with an offline measurement, your motor or generator is out of service and the power cables are disconnected and being isolated. But what is more important is that your winding is at room temperature and you have a cold conductor. That means thermomechanical effects, which you can find only in fact during online measurements, you won't see immediately in an offline measurement unless there is already some decent deterioration of the insulation material. So for instance, looking at slot discharges where you have probably loose wedges. Loose wedges, they are important then to see, okay, what is the rated power and also and actually the proportional magnetical flux. And if the power is increasing, the magnetical forces in the air gap between rotor and stator, being the magnetic flux, is proportionally increasing. That means the bar tends to vibrate. And during normal vibration under operation, the diameter of your straight part is being reduced by the continuous ongoing PD activity, which eats up the insulation. So this effect of this vibrating bar you see pretty good online. If you measure this offline, what you basically see is more or less the same pattern, so triangular pattern with dominance in a negative half cycle and a triangular pulse distribution. But you see only slight evidence if the slot corona prevention layer has already been affected. So you see some things, some phenomena, what you can derive from an online and an offline measurement, but it's not always the case because some partial discharge effects are purely load bonded or only detectable under real life conditions. But the offline measurement is then actually the right tool to serve as an in-depth verification to find signs of partial discharge phenomena that are ongoing during normal operational conditions. So that's more or less the answer on this question. So the major difference is again offline, you have a cold conductor, you have the same field distribution in the entire winding, and during an online measurement we have a 3-phase field with 120 degrees phase shift. That means also introduced potential differences in the face-to-face barrier insulation. And you have a warm winding, so the thermomechanical effects are more pronounced in an online measurement than in the offline test.
All right, thank you. Also, Jeroen, can a PD pulse be bipolar? Are unipolar and bipolar PD signals interpreted different?
Well, with the instruments of power diagnostics, we have an advanced triggering mode, and we have the capability to both show a unipolar pattern where basically the positive and negative pulses are summed up and shown as a positive. And we do have the bipolar mode separating the positive and negative counts. So this is just a matter of not making any mistake in testing, but this is just how the user behind the instrument wants to have his patterns accumulated and what is the most convenient way for that person to do the analysis. So basically, you don't make any mistake. It's just how you want to get it. And the advantage of course, doing the bipolar measurement is that you can see more relations in signals and so on. I mean, if you're really looking at positive and negative counts and statistical analysis and these kind of things, a bipolar measurement is probably more preferable, but basically both measurements say the same. So you're not missing anything or doing anything wrong when you measure bipolar or unipolar. So it's up to the user itself and how comfortable he feels with the way of detecting.
All right, thank you. Charles, is it possible to establish a relation between offline and online PD tests? Are those results comparable?
It's a little difficult to establish a full relation between the two, as Jeroen just mentioned earlier. There's different conditions such as your no load or cold conductor condition, and there's going to be slight differences, though the results will be comparable on your phase resolved partial discharge patterns. The difference between your online and offline tests are going to show some slight differences just due to the fact that some areas are going to be stressed differently between or the electric field is going to be distributed differently between your offline and online tests, which are going to show some differences in your phase resolved partial discharge patterns. More or less, though, they should be comparable, but you're going to be able to see some differences between the two.
All right, thank you, Charles. Is offline PD measurement applicable for 4,000 volt motors?
Well, Michael, that's a good question. So in the literature, there's a lot of, so to say, information going around that PD measurements are only suitable for machines with a rated voltage of 3 kV and higher, because basically they're considering the inception voltage being 3 or 2.7 kV a centimeter at atmospheric conditions. Well, I can tell you that looking at rotating machines where the partial discharge generally occurs in a trapped gas inclusion, that you have to consider the breakdown strength of air, which is 30 kV a centimeter. Recalculating this into millimeters, we talk about 2.7 kV a millimeter. And when you would rework that into micrometers and so on, we are ending up with voltages of 270 volts. So it's just a matter how the internal field strength is and what is the size and geometry of the air bubble or delamination inside the winding. That means, yes, on a 4 kV stator, you can have partial discharge. What is, of course, important to know is how is the construction of the winding. Does the winding come with end winding semiconductor field grading or only conductive slot corona prevention layer in the straight part? Because, of course, you might get partial discharge patterns pointing to, for instance, a field grading problem by the absence of field grading, which is generally first applied from 6 kV onwards. But on the other hand, you can perfectly detect internal problems, internal delaminations, thermal aging. So yes, I'd say you can measure it on form wound windings, but you need to have a bit of background of what kind of a winding is inside. And especially looking now at frequency controlled motors, so inverter fed machines, there you have like peak voltages between the face-to-face barrier insulation, which can be 6 to 7 times rated voltage. So even for a low voltage motor, this can induce partial discharge. And so therefore 4 kV is definitely not a limitation for form wound windings. And also keep in mind or just know that PD measurements are these days requested as well for type 1 and type 2 inverter fed low voltage machines. So yes, it's possible. Definitely worth it to implement it in the maintenance strategies.
Right. Oh, and I have a follow-up question for that. Is there value in carrying out partial discharge monitoring on apparatuses operating below 5 kV, such as 3300 volts?
Well, permanent monitoring is actually something that is in the focus of condition-based maintenance done on critical assets. And if you have like a 20 megawatt 10 kV motor, the motor you are naming here, rated 3.3 kV or below 5 kV, can be of the same importance than the big one. So it's making an assessment of, okay, do we really want to go for monitoring, yes or no? And how important is this machine for my production loop? But in the first first recommendation from my side is that actually a fairly good compromise with every new motor is that, first of all, you need to have the factory acceptance measurements for PD and tan delta during the production stage, which is basically your reference value for the future. And what you can do is from the very beginning install capacitive couplers in the terminal box, which allows you to connect online. And if you start to see something in the consecutive offline measurement during the next major turnaround, or you see an increasing trend or a developing PD pattern during periodical online measurements using these coupling capacitors, then the next step could be to decide for continuous monitoring. It's maybe a bit like on a transformer. As long as your DGA results are good, there is actually not an immediate additional value to have PD monitoring right away. So first, if you start to see signs between offline measurements using the same equipment and same setup versus the reference measurements you had during the FAT, or you see some significant trends in the online periodical tests using the couplers, then it could be worth it to install PD monitoring. Answering the question again with the voltage level of 5 kV, well, it's just a matter of how important is this asset for my production loop. And this is a question I cannot answer in general. So that's to be evaluated by the asset managers for the maintenance. Huh? So, but it's possible, definitely.
Thank you. Charles, Is there a paper or books about the patterns of the PRPD?
So the standards that I had mentioned are in the normative references. So the IEC 6034 and the IEEE 1434 both have examples. For instance, in the IEEE 1434, Annex C is a typical partial discharge phase, pulse phase patterns, and the Annex D and E also provide some examples of phase resolved partial discharge pattern, and actually go in and discuss what the different patterns mean and how they are derived, or how the assumption from the defect is arrived. So I would reference those normative standards that I mentioned if you would like to look up some typical PRPD patterns and get some more clarification about those.
Thanks, Charles. While I have you, what are the main differences between ICMsystem and ICMflex in terms of equipment and software?
So in terms of equipment, the ICMflex really contains, I mean, it's a stationary instrument, as we saw, and the acquisition is on the high voltage potential. Additionally, what's used is just your high voltage line filter with using the ICMflex, and that's really just the two things that you would need in terms of that. With an ICM system, the setup is slightly different, and the fact that the coupling capacitor for the ICMflex is part of the column of the ICMflex, where the ICM system you would need an additional or separate coupling capacitor from the measure or the PD instrument or detector itself. So the setups are identical or very similar, but the equipment is slightly different in the fact of what you use. As far as software, the ICM system is capable of in-depth. So as we saw analysis, it's a parallel channel instrument, so you have simultaneous updated multi-channel panel, and with the ICMflex, you're capable of performing your tan delta and capacitive measurements, as well as your partial discharge at the same time. So that kind of gives you a benefit of performing those two there. So there's some differences there.
All right, as a follow-up, is it possible to test medium voltage cables with ICMflex, and will the results be relevant?
Sure, absolutely. So the ICMflex is also capable of testing medium voltage cables while performing partial discharge and tan delta measurements as well. So, and those results would be relevant. Those results would be useful as far as just performing a tan delta or power factor measurement with any other instrument on your cable, and partial discharge testing. So it's definitely beneficial if you have joints or other accessories within your cable that could be revealed with those measurements. Partial discharges, or tan delta rather, or power factor is more of an average measurement and kind of gives an overall assessment of the condition, where partial discharge has the opportunity to find some of the isolated events. So definitely relevant and capable with the ICMflex, yes.
All right, thank you. Jeroen, can we use VLF test sets for PD measurements?
Yeah, that's a good subject. So very low frequency is a well-known test technique for cable testing. Medium voltage cable tests as actually perfectly fits also with the previous question we had. Our ICMflex and the ICM system are able to synchronize on VLF frequencies. So basically the equipment is prepared to do a measurement at either power frequency or VLF frequencies. The only thing what should be considered, and I luckily made my thesis about that a couple of years ago, is that there are significant differences between a very low frequency sine wave and a power frequency sine wave in terms of polarity effects. You have a different permittivity, which is frequency dependent, and that means actually that you have not comparable results, are not a specific factor between results acquired with VLF or with power frequency. But if you use the measurement technique for trending with the same setup with the same equipment, you can use VLF test results as baseline. The only thing what I can add is that some partial discharge phenomena will not be revealed using VLF. because the VLF frequencies are transparent, more transparent for some insulation layers, which are also frequency dependent within the rotating machine insulation system. But in general, you can use it, but with some limitations. And main message is, don't start to compare power frequency results with VLF results, because you won't find a factor for the tan delta. And for the PD measurement, you should consider that when you measure like 30 to 60 seconds for a measurement with power frequency, that when testing with VLF frequency, in order to have a PD pattern with at least a similar amount of events, a similar amount of counts, and similar pattern properties, you will require a testing time which is about 1000 to 1500 seconds per voltage step. So the testing time will take significantly longer. And again, to make a long story short, it is possible. It is possible to do it, but don't start to compare power frequency results with VLF measurements, because there is not one straight line in this.
All right, thank you. Charles, is there any additional benefit to the tan delta over offline partial discharge testing?
So there is a benefit, because your tan delta test, well, it's not really over. There's a benefit to performing both of them. I don't think that there's a benefit to performing tan delta over partial discharge, because tan delta measurements or power factor measurements are going to give you, as I said before, an averaged condition assessment of your insulation. So it will give you the condition overall of your insulation system, whereas partial discharge testing has the ability to find localized defects, as we saw with spherical voids and delaminations and such, and you're not going to be able to identify those, or at least I should say they would affect your tan delta measurement, but you wouldn't be able to pinpoint and say that I have this problem as you would with the partial discharge measurement. If you were to look at the phase resolved partial discharge pattern, for instance, with the spherical voids where we saw those arcs and we were able to count how many voids we had, we know at that point what the fault is, and you can determine your condition-based maintenance program over that. Now, with your tan delta measurement, it's going to give you an average measurement, whereas if you have a critical problem, that's a good point. If you have a critical problem within your insulation, then and the rest of the insulation is perfectly fine, your tan delta measurement may come back acceptable, maybe even good, whereas your partial discharge measurement will give you insight into that defect and would let you know that it is in a severe location and it needs some attention, whereas in your tan delta measurement, you may know by the time it's a little too late. So I wouldn't say that there's benefit over one over the other. I think that they complement each other, if I had to say that.
So Huron, I have a motor that's 13.8 kV, and we have to perform PD tests offline. So how can I select the proper coupling capacitor and filter?
Yeah, first of all, Michael, you have to look into the rated voltage of the application. So 30.8 kV, you can make with a CC14B for online applications, or with the CC20B for offline applications. But the coupling capacitor, preferably for offline measurements, is in our product range from Power Diagnostics 1 nanofarad, which is sufficient to detect problems from deep inside the windings. The filter is actually to be calculated according to the capacitance. So what we need to have is an approximate estimation of the coupling capacitor capacitance range, where we can then calculate the capacitive impedance and the required current, because the current is important for the filter. So if we have an idea about the current, then we can say, okay, from our filter range, generally the lowest voltage we have is the 30 kV range. 30-1 or T30-5 filter. The 1 stands for 1 amp, the 5 stands for 5 amps, and we also have them in 10 and 20 amp range. So main thing we require is actually the maximum test voltage, what is intended to be applied, and what is the approximate capacitance of the test subject, which allows us to make a calculation of the power consumption, and hence actually the required current, which is then important in return for the filter design.
All right, thank you. Charles, can we measure at the same time motor, tan delta, capacitance, and PD with the ICMflex?
Yes, it is capable of that, and it does have the multi or simultaneous update as well. So the ICMflex is capable of performing your tan delta capacitance measurement as well as your partial discharge measurement. And that's kind of one of the advantages for the ICMflex with testing rotating machines is you're able to get all three of those key measurements. So it is capable of performing those measurements at the same time for your motor testing.
Thank you. As a follow-up, is it possible to use the same PD measuring device for different applications, such as rotating machines and transformers?
Absolutely. So just touching on some examples, what we had mentioned earlier from a previous question, that the ICMflex would be good for testing cables as well. And that is true that the ICMflex would be a good choice for either cable or rotating machine testing. And on the other hand, we have the ICMsystem that we talked about, and the ICMsystem would be a good choice, for instance, if you wanted to do maybe factory acceptance testing on power transformers and you needed those additional channels where you have up to 10 channels with simultaneous measurements that could cut down the factory acceptance testing times. So definitely the instruments are versatile and they are capable of measurements on different applications other than just rotating machines and transformers as well. So that could include switch gear and so on. So they are very versatile in the fact that they are capable of measurement on different apparatus in your substation.
All right, thank you. Huron, as online is with 80 PF and offline with 1000 PF couplers, can we compare these two?
Well, the 80 picofarad online couplers are referring, I guess, to the nice coupling capacitors from our colleagues from Iris Power. So they have these 80 picofarad EMC couplers, which generally are actually designed as a first order filter, looking at the 80 picofarad of the capacitor and the 50 ohm impedance of the cable. It brings it to a corner frequency of 40 megahertz. And when looking into this frequency range, you are able to find problems close to the bus duct system and possibly the first line side bars of your phases. But problems more deeply buried inside, the signal will unlikely be detected by these kind of couplers. On the other hand, when you measure online with a 1 nanofarad coupler, you can generally be sure that you nearly cover from line end to neutral end. And if you don't feel comfortable or if you're unsure about the coverage, I'd recommend to put 2 coupling capacitors, so 1 on the line side and 1 on the neutral end. Do a calibration from both ends, and then you see the signal response from line side towards neutral. And this confirms you if you basically cover the entire winding either with 1 or with 2 coupling capacitors.
Thank you. While I have you, if I'm getting all types of PD patterns in one plot, how can I say which PD is the dominant PD?
Which PD is the dominant PD? Therefore, it's as Charles explained also during the presentation. With an offline measurement, you increase the voltage stepwise, and that means you will also have to look at the PD level and pattern proportionally. That means continuously looking at how the PD pattern develops can provide you, for instance, with increase of the test voltage, can provide you different phase resolved PD pattern properties, which then all point to a specific partial discharge activity. So message number 1, slightly ramp up the test voltage and monitor accurately what happens with the phase resolved PD patterns. And this way you can unveil or reveal different kinds of PD activities which tend to incept at different test voltages. On the other hand, what you can do as well is look at the spectrum, and some activities will come up with a different in a different bandwidth, And that means if you perform measurements also, if you look at the overall spectrum and shift your center frequency cursors along the spectrum, it might be that from one common pattern, you can filter to maybe 2 or 3 individual patterns showing different types of PD activity. Which one is the dominant one? Well, you can basically look at the magnitude, but if you shift the frequency along the measurement, your calibration is not valid for the full range. So it's generally looking to which type of activity produces the most dominant pattern properties in your result. And there, from analysis of the phase resolved PD pattern, you can determine which kind of activity is the most critical one. And if you feel uncomfortable with results taken only from the line side, you can repeat also the measurement from the neutral end, or you can measure with a neutral connected or the phases separately to introduce different field strengths or different field distributions in the winding, and then you can probably even more detect more different or dominant activities. So again, the main message is look at the phase resolved PD pattern and follow how the properties develop accurately versus raising test voltage.
All right, thank you. Additionally, I have a question for you. What is the best suitable PD coupler used for PD measurement? 80 picofarad, 2 nanofarad, or 10 nanofarad?
This is an excellent question. I really like them. The thing is, each manufacturer of PD equipment has its own philosophy. But what has already been proven several times in the literature is that basically the signal contents of partial discharge, so to say, more deeply buried within windings, provides a frequency contents up to 10, maximum 20 megahertz signal bandwidth. That means you have to modify the coupler and the corner frequency or the cutoff frequencies of the couplers as such that they focus in this frequency range. That means measuring in a too high detection bandwidth may often give results indicating 0 picocoulomb or 0 millivolts, simply because the coupler doesn't capture the activity traveling from inside the windings towards the coupler, and the attenuation between the point deep buried inside, or the cavity deeply buried inside the winding, traveling up to the line side terminals where the coupler is connected, suffers too much attenuation and remains undetected. Basically, to answer the question once again, is the input sensitivity of a coupler is not only depending on the capacitance, but also on the impedance. And for instance, roughly comparing a measurement with an input impedance of 50 ohm versus an input impedance of 1 kilo ohm, is factor 5 in signal strength. That means basically you can have a 1 nanofarad coupler with 50 ohm impedance and a 220 picofarad coupler with 1 kilo ohm. It gives the same signal strength just when playing with the input impedance. So if you have an online application where you have a very compact motor terminal box, I would rather go for the low compact coupling capacitor, which provides in case of power diagnostics the same signal strength as a 1 nanofarad coupling capacitor for offline measurements. Some of our competitors, they say we need to go higher in coupling capacitor value, so 2 nanofarad and even 10 nanofarad, because they work with 50 ohm. But the philosophy of power diagnostics is that, okay, let's play with the input impedance to create the same signal strength in order to have a more compact, lightweighted, and at the end, cheaper coupling capacitor. So it's not only a matter of capacitance, but a combination of capacitance and impedance of the decoupling circuit.
All right, thank you. We have time for one last question, and it's going to be for Charles. Does Megger PD equipment show the result in picocoulomb or millivolts?
This is a good question, Michael. So it depends really. The instrument is capable of either, but picocoulomb. So it depends on the measuring bandwidth that you're doing. So the picocoulomb refers to the IEC 6270 calibrated circuit within that bandwidth, so less than the 1 megahertz. Once you start to deviate, or rather, once you start to go past that, then you can't strictly follow the IEC 6270 calibration procedure, and therefore you cannot necessarily relate that to a picocoulomb value, and therefore you start to show the result in the millivolt. So the instruments are capable of either, but it depends on the test that you're performing and which bandwidth you're utilizing. So if you were to perform the measurement outside of that, then you wouldn't measure so much in the picocoulomb value, but rather the millivolt value. Or if you were to perform maybe an acoustic measurement or an electromagnetic measurement, then also that would change as well from the picocoulomb value.
All right, thank you, Charles. It looks like that's all the time we have for questions. We apologize if we didn't get your questions today. We had scores of phenomenal questions that we are going to follow up with you offline in the following weeks. We just didn't have time to address them all today. But once more, a copy of the presentation, certificate of attendance, and a link to the video recording of this webinar will be emailed to everyone in 2 business days. I'd like to thank you all for attending. If you could please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. But again, I'd like to thank you all for attending, and I wish you all a happy weekend.